Okay, our next speaker going to be Patrick Lodeweegs. So he will speak about the effect of policy attacks on casual universal learning. Patrick, please.
Perfect. I just started my PhD at the Radboud University, and I would like to tell you in the next couple of minutes about the effects of poisoning attacks and causal deep reinforcement learning. This is a topic I worked on in my master thesis under the supervision of Stjepan and Gerrit. So I would briefly like to start with a short introduction, some background terminology or methodology, and the results and limitations of our. So, as you are all probably aware, machine learning can be used for a lot of different applications, but some might be quite sensitive. For instance, because they make important decisions about people or handle sensitive data. Therefore, it's important to not only look at the accuracy of models, but also look whether they are trustworthy, so if they are fair for everyone and if they are actually reliable. One major threat that we just heard in the previous presentation to this trustworthiness is adversarial attacks. And adversarial attacks, there is some kind of adversarial party that tries to, for instance, with noise, introduce samples that shift the decision boundaries in the model. As we also heard previously, there are a lot of different defenses against it, but most of them have trade-offs that they reduce performance, even if there's no adversarial attack happening. Therefore, one promising research direction might be the introduction of causal machine learning, where we try to not only look at the correlations of data, but to the underlying causal distributions of data. Because these adversarial attacks mostly work by introducing spurious correlations in the data, which should not impact the underlying causal distribution. However, this is also not a magic solution, of course, because inferring such a structural causal model is quite hard. And in practice, we mostly don't know it a priori. If we don't have the full causal model, we might still miss some variables that are not modeled in our environment, which then can lead to, for instance, the same spurious correlations and try to avoid in the first place. So next, to make sure we are all on the same page terminology-wise, we looked at reinforcement learning models. So traditionally, these work by an agent that interacts with the environment. So we don't need a labeled data set for similar to supervised learning, but instead learn directly from these interactions. Another advantage of using reinforcement learning is that these interactions enable the learning of sequential decision making. So that means that previous actions influence the environment, which allows the agents to adapt to changing. And this study is specifically focused on deep reinforcement learning, which is basically a combination of the traditional reinforcement learning paradigm with deep learning methods in the agent, which allows the agent to reason about more complex, for instance, higher dimensional observations. So next, for the adversarial attacks, we can roughly classify these in three different categories: confidentiality, availability, and integrity. We mostly focused on availability with untargeted poisoning attacks. The goal of these attacks is to introduce some noise before training in the data. So this noise then changes the decision boundaries during training, which will reduce the performance in general during inference. So that means that even though the data used during inference is just the normal data, it will perform less compared to a model that has been trained with the clean data instead of the poisoned data. Next, I would like to briefly introduce our methodology. So I will start with the models that we applied. So we looked at three different models: DDPG, CDT4X, and NCDT4X. DDPG is a well-known reinforcement learning model that uses the actor-critic architecture and is online. So that means that it basically works like a typical agent environment paradigm that you would expect from reinforcement learning. CAT4X is a new model that uses causal decision transformers to use that causal information, and in our hypothesis would be a bit more robust against adversarial attacks. This model is an offline reinforcement learning model. So that means instead of using the typical agent environment interaction, we first collect interactions and then use these to train the network. This is the advantage of being able to use previously collected data, which might be beneficial in some fields where you cannot directly experiment with an agent in the real environment. For instance, in a medical setting, it might be quite desirable to first explore random actions to train a model. And as the third model, we looked at NCDT4. This is a small adaptation of CDT4, where we basically remove the causal part again, which allows us to more directly compare the impact of this causal layer of the adversarial robustness. So we evaluated 6 different adversarial attacks. Most attacks were only reward poisoning, so that means that we only change the reward that was observed by the agent after a step. We used initially constant reward poisoning, so there we, for instance, set a reward to the minimum naturally occurring value in the environment of 0 or the maximum of 10. But we also tried this unbounded and bounded reward inversion, where we simply invert the reward value. So initially 10 become -10, while 0 remains 0. Or in the bounded variant, we have 10 becomes 0, 0 becomes 10. The main advantage of the bounded variant compared to the unbounded one is that the rewards stay in the same distribution. So for a human observer, it might become quite obvious that something fishy is going on if you expect values ranging from 0 to 10 as rewards and you suddenly get -10. We also looked at 2 extensions to the bounded reward inversion attack, state and reward poisoning and clustered reward poisoning. For state and reward poisoning, we not only poison the rewards, but also the state, as the name implies. And I will get back to these 2 attacks in a minute. So to briefly walk through some of our results, we initially started with measuring the clean performance. So this is without any poisoning attack going on. So we measured this in the vertical Tajalli environment. This is a simulator used to train recommender systems over data from the Tajalli online shop. And in this environment, we use the click-through rate to measure the performance. In this case, a higher click-through rate means that our recommendation causes more interaction, which we will regard as better. And we measure this for 100,000 episodes, where we define an episode as a sequence of steps before resetting the environment again. So as you can see for the clean data in orange, DDPG performs best in our training. Well, there's still clear difference between CDT4 and NCDT4, which strongly suggests that the causal layer actually helps in the clean setting. And we see something similar actually when using the adversarial attacks. So for the maximum rewards, we see that in general, CDT4 and NCDT4 perform similar. While DDPG suddenly performs worse. The same picture we also see for minimum rewards on the side of the screen, where besides some outliers, performance stays quite similar. We see more differences for the reward inversion attacks, especially for DDPG. You can notice that the performance actually drops quite far, the relative CTR score, to close to 0 for high poisoning rates. Basically means that the model is producing worthless recommendations. Well, for the unbounded reward inversion, we see that NCDT4 specifically performs surprisingly bad, which suggests that this model is somehow more vulnerable for these outliers outside of the normal reward distribution. Then, as promised, to get back to the state in the reward poisoning. So this was an extension to the bounded reward inversion attack, where the results are shown again. So the same graphs side by side. As you can see, there is quite a big difference for especially DDPG. So what changed within these two attacks is basically that instead of only poisoning the reward, we now try to poison the 5 most impactful states. We selected for 5 most influential features of the state. We selected these features by doing a linear, comparing the linear correlation coefficients and selecting the 5 most correlating ones. And this seems to, especially for DDPG, perform quite surprisingly better. For clustered reward attacks, we try to be a bit more smart which interacts with poison, because for all other attacks previously discussed, we used random interactions poison, but in this case, we tried to poison only certain outliers. So we first clustered into a high and low performance, high and low state performance clusters. So we have clusters with states where the observations almost always lead to low rewards and the other way around. And in this case, we take outliers. So in the cluster of the high performance states, we wanted to poison the ones that perform badly, and for low performance states, the other way around. And we use this to poison the CDT4 and NCDT4 models. And for low poison rates, you can see that, especially for CDT4, quite different between the normal reward inversion and the clustered reward inversion. It suggests that this approach might be beneficial for lower poisoning rates. So to wrap up, we tested 3 models with 6 different attacks. For all models, we saw some impact for poisoning. However, our measurement setup was not the most stable one. So future work would be needed to expand this measurement setup, for instance, to also account for non-deterministic behavior during the training phase. Overall, we can say that DDPG is the most vulnerable, but that we did not see much difference between CDT4 and CDT4. So to get back to the main research question, we could not confirm our hypothesis that causal machine learning in this specific application seems to substantially improve the robustness of the model. So with this, I would like to thank you for your time, and I will be willing to answer questions.
Thank you very much for this presentation. So it's you want to have any question? Okay, I'm not sure what you're saying. You know what's happening? You make it's not really something that's or maybe work with this.
Both. Yeah.
Okay. So you change the rewards. You change the rewards to make that also overshot.
During the training in general.
So the so what kind of mitigations do you think
We hope that the causal machine learning itself will be a mitigation for these attacks. But there are many different mitigations already described in previous literature, but we did not specifically look into that for this study.
Okay. Any other questions? Okay, let's finish this meeting.